So flip this page. So the nodes, so you have that blank there, nodes, oh you have it. Nodes are the points in a standing wave where there is minimum amplitude between the two waves. So that's like where it appears to be stopped. And to remember that, no displacement. So it's like it's not moving. No zzz, no displacement. Nodes. Okay? That's how to remember. Then antinodes are the points in a standing wave where there is maximum amplitude between the two waves. So that's like where our crests and our crests meet up, or our troughs and our troughs meet up, and we have that interference, that constructive interference. So here is a diagram of, say, like those two guys holding the spring and making the spring move. And the wave will go up and down, but it appears like this wave goes flip-flop, 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 right? And this would be like the nodes where you could touch it and it would still work. So here this diagram shows you here, like at each point, this is an antinode, that's an antinode, okay? Antinode, so you should write it in, antinode. And then each spot like here, that's a node. So the antinodes flip up between being, this is like the constructive, this is like constructive interference of crests, and this, use a different color, this is the constructive interference of troughs. Okay, so now, if we understand this standing wave theory, we can apply it to different situations. So nodes will always occur at fixed or closed ends. That's very important. So I would underline that. Nodes or fixed, closed or fixed ends is where the node happens. It happens in between as well, but there will always be a node at the ends. Okay? There's always nodes at the ends. Antinodes will always occur at open ends, or if it's free to move. So, for example, say we have like this would be an air column, and it has an open end. So at the top we have an open end. At the bottom it's like a closed, the water's acting like the tube is at a closed end. Okay? So say this tube, if we had sound waves moving down it, at the end would always be a node. Okay? So it's like we have a wavelength comes down and it's reflected on itself at the exact same frequency and probably same amplitude. So how much of a wavelength is what I just drew here? Is it one wavelength, a half a wavelength, a quarter of a wavelength? Which one? Half? Okay, let's think about our waves. So if this to this is a full wavelength, this to this is a half. So we're only going, yeah, I thought it was a quarter. It's a quarter, this one is, right? That makes sense. Yeah, so this is a quarter of a wavelength.
Wow, it's going down again.
Wouldn't it be a half?
If I'm looking, oh, I should say here, if I'm looking, it's just this coming down. That's only a quarter of a wavelength. You only count like one coming down. Because it's like that's the one wave, and this is the wave being reflected. So if I'm just looking at this wavelength, this is a quarter. Up here, since this is an open space, this is the anti-node. And here would be a node. Okay, so then now if we have an open-ended tube or air column, so there's no end, like if it was just like this. If we drew it going through like that, each end needs to be an antinode or it to be open. So here we have antinode, here is antinode. If we looked at just the length of, say, of one wave coming in, that is half of a lambda. Just one wave coming in, not the reflection. And then here also we can identify this as the node. Here's the antinode. Here's the antinode. So because of this, our antinodes and nodes, we know that springs and air columns or tubes will have a natural / resonant frequency. Because there will be wave interference where it's being reflected back at the nodes, and you can get that mechanical resonance. So this mechanical resonance, so because of this, mechanical resonance can be achieved when a force frequency matches the resonant frequency of that object. So when a person blows over the top of an empty bottle or blows air into an instrument, the air starts to oscillate or vibrate and actually produce a standing wave. So I did it earlier. Right? Oh, that's fine. Okay, then this one. Don't worry. Why do they sound so different? What's different about these? The what?
Size.
The size. What does the size change? The sound. Why? What changes? Well, I guess we can answer and see. It's going to change the actual wavelength. Okay, so resonance is heard at the points of constructive interference where the maximum amplitude will produce the loudest sound. So I needed to find the right type of force to blow into the bottle to have the right frequency. Okay? What I was searching for when I did that was the right frequency to have a force frequency to resonate it. And the angle. Okay? Now this is your answer. The resonant frequency of the note or notes are produced depends on the length of the air column. So that resonant frequency, it's the frequency that is different. And that is changed with the length.